Good morning, everyone. I'm Rose. I'm a PhD student here at Concordia, and I'm going to present part of our literature analysis for our research on automated crack recognition. Identifying cracks is one of the most important part of inspection in concrete infrastructure. Currently, the conventional way of doing inspection is manual, which is costly, time-consuming, and poses safety risks to the workers. And therefore, there has been a shift towards more automated ways of doing inspection using drones or UAVs. So in such automated methods, there's a need for detection of cracks from the image data. Vision-based crack detection has been studied within the field of computer vision for some time, and recent years within the deep learning, where the focus is on designing and training models that can extract features from input image data, and they can learn to predict whether the sample is a crack or non-crack. So this prediction can be done at different scales, for instance, at the image scale to classify the whole image, or identify approximately localizing the crack object. Then the third one is the semantic segmentation, where we can identify cracks at the pixel level. So with semantic segmentation, we are able to further analyze the detected cracks to, for instance, measure the dimensions of that crack. So that is why this is the task we focus on in our research. There are some challenges with this task. One of them is that cracks do not have any regular geometry. They have a non-rigid shape and they can appear at different scales. So we need models that can be as accurate as possible. They can be robust to new environments and scenes, which we call generalization. And then also they have to be fast so that we can use them for near real-time applications. So the question is how we can achieve this. So that's why we started with a comprehensive literature analysis to have a better understanding where are we at in automated crack detection and find out the challenges. I'm gonna skip this. So our literature analysis is composed of two parts. The first part focuses on the crack detection itself, and then the second is the crack quantification. So in crack detection using deep learning, we have two main tasks. One of them semantic segmentation, the other is curvilinear structure segmentation. And then the third approach, the third part is the learning approaches, whether we are going to have supervised learning, semi-supervised, or unsupervised learning. So I'm going to go through them just quickly. So in semantic segmentation is the dominant approach, and many models have been designed and developed in the literature using different architectures, starting from convolutional neural networks, vision transformers, and recently vision mamba. And also hybrid models have been also studied. These are some samples of the developed architectures. And the second is the curvilinear structure segmentation, where the focus is on identifying objects that are curvilinear, such as blood vessels or cracks. So the challenge with such models is that they are sensitive to noise and their scalability is a real challenge. And the third part about the learning modes, first, supervised learning has been studied widely, and the challenge is the scarcity of annotated crack data sets in the field. And then also we have semi-supervised learning, which we can leverage from both the labeled and unlabeled data. But then again, the challenge is to how to preserve the accuracy. Recently, some novel representational learning frameworks have been also developed, and which they can leverage from both supervised and unsupervised learning for different part of the image. But then their computation cost is also another challenge. So for crack quantification, three main methods we have in the literature. The first one is medial axis transform, where the skeleton of the detected crack will be extracted. Then we can measure the width. Then we have, for instance, Euclidean distance to measure the Euclidean distance of different part of the detected crack. And then we have a third method where we can divide the area of the crack over its length. So the challenge here is that these methods are not tailored for crack detection, so they are really sensitive to noise. And Yeah, so they're sensitive to noise, and the quality of the segmentation mask is really important for this part. So that's why we need a better segmentation models. So for segmentation models, the challenge is that the models show really high performance in controlled environments, but not in the wild, not in practice. And then also another challenge is the trade-off between the computation cost and their inference speed. So more needs to be done within this area so that we can get to the point that we can apply such models in practice and then rely on that. So yeah, like I said, the main point here is to optimize this trade-off between inference speed, accuracy that we want, and the computation cost. So recently, with the emergence of vision foundation models in computer vision, we have there has been a revolution in computer vision. These are larger scale models that are pre-trained on larger scale data sets, generic data sets. So they have learned rich representations and they're really suitable for adapting to downstream tasks. So one of them, so the Vision Foundation model for semantic segmentation is a segment anything model. Uh, these models are based on their backbone is based on vision transformers, and there's a lot of challenge empirically and theoretically in adapting them to such downstream tasks. So that's why in our recent study, which is under revision, we have introduced and proposed an efficient selective fine-tuning method. And then we developed the segment any crack model based on the backbone of segment anything model. Our results show the transferability of our proposed fine-tuning method to several other segmentation models, which gives us a higher accuracy and a better efficiency in fine-tuning and adaptation. And then also our results show the superiority of our segment and crack model over 7 state-of-the-art segmentation models. So the paper is currently available in ArcSci. You can check it out. And yeah.